Hi there, this is Chris, and what I wanted to do was I wanted to start out lecture 13, which is Assembly Language Part 4, by going over the actual example recursion that we looked at in the end of Friday's lecture. And if you haven't seen the updated version of the end of Friday's lecture video, please watch that first as I go into some more detail about the recursion that is kind of important for what we're about to talk about here. So here's what I've got. I have the factorial function that we looked at before, and I've actually printed out what GDB actually created, or sorry, what GCC actually created. And it's a little different than what we looked at on the previous slide. There's a couple extra instructions in here. I'm not exactly sure why GCC did it this way versus the other way, but we're just going to go over what it looks like, and then we're going to actually take a few minutes and look at all the details about what's happening to the stack during this recursive function so that you can really get a feel for what's happening in that. So let's take a look at here. What we've got is we've got this function that's going to take the parameter and it's going to calculate the factorial for the function. In fact, the one we're going to look at is going to be 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. That's what we're actually going to look at. And let's see what the assembly language actually does. Well, the first thing it does is it says, I'm going to just simply do this comparison right off the bat. I'm going to compare 1 to the parameter n here, and I'm going to, if n is less than or equal to 1, then I am just going to jump all the way down to here. I am going to set the value 1 into the return value of EAX and then return. Now, this kind of gets jumbled up inside here. We actually have another jump that jumps right over here. Why the compiler did it exactly like this, I'm not sure, but let's just look at what happened here when it comes out. Okay, after it does this first check, then it immediately pushes RBX. Remember, RBX is a caller-owned register, which means that if we're in a function that was called, we need to, and we want to use RBX, we have to store it and then return it to its original value at the end of the function. Okay, and we're going to see how RBX actually gets used as we go through the example here. Okay, what does it do next? Well, it stores n into RBX. Okay, it's going to store that for later. And then it's going to subtract 1 from n and then call our factorial function. Well, that's all this going on here, right? This is saying, okay, we're about to do the factorial of n minus 1 over here. Okay, so once we do that, RAX will have our factorial of n minus 1. That will be an RAX. So what are we going to do? We're going to multiply the value we stored as n times RAX, and then we're going to jump over this little stub here, return RBX to its value, and then return, which means RAX is going to hold the actual value of n times r factorial, and that's what we're returning. Okay, so let's actually go look at what GDB does with this. Okay, so let's look at the GDB breakdown of our function. Okay, so what we're going to do is we're going to open up our factorial in our in GDB. Okay, then I'm just going to break on main and I'm going to run it. Okay, and then I'm going to do next, and then we're about to call our factorial function here. Let's actually do this. Let's disassemble main, and we're going to look at this, and what it's doing is main is about to move 5 into EDI and call our factorial. Great, that's because it's going to move 5, and we're calling factorial of 5. Okay, so we hope that at the end of this, RAX needs to hold the value 120. That's our ultimate goal. Okay, so we're about to do this. So in GDB, we're going to step into the next instruction here, and we're going to do that. Now, let me actually start displaying some things. Okay, first thing we want to do is we want to display /4i $RIP. That will give us the next 4 instructions that are in the next order of instructions. Okay, let's actually also display our RDI value. That's 5. That's our parameter that we're about to use. Let's display our RAX, which is going to be our return value. Right now it's garbage, 4195678, that's just garbage. Okay, and let's also display the stack pointer. Okay, the stack pointer right now is going to be on E9A0. Okay, and I'm going to draw this in a second, and we're going to see that. Let's actually display the result of, let's actually display the actual value of RSP, and we'll do it in two different ways. We'll display it as a long star $RSP. We're going to dereference it, okay, and it's just going to give us a decimal value. We're also going to display it, and you'll see why in a minute, in hexadecimal, in the exact same thing here. Long star $RSP in hexadecimal, okay? And then let's also look at, make sure we display our BX, because that's, we're going to be using that as we go along. Okay, so here's where we stand right now, okay? We are about to call, we're in main, and we are about to call our factorial function. We'll take a look at that in a second, okay? And then these are all our variables. So let's actually draw some of this, okay? Let's actually draw some of this. We'll do it kind of like this, and we'll put a whole bunch of, let's say these are all 8-byte dividers here. Not exactly sure how many we'll need. We'll need a bunch here because we're going to do the factorial function, which is recursive. Okay, so let me just put a whole bunch in here, like this. Okay, and there we go. And right now, RSP, let's just do this, RSP points to the value, let's see, RSP, it says, is E9A0. I think we can just leave it with E9A0 there, okay? And what it actually holds, as it turns out, is 0. Not too important right now, but that's what RSP points at, and that's the location, okay? All right, what else do we have here? We've got RDX, which has the value of 5. That's the, nope, sorry, that's RDI has the value of 5. There we go, okay, RDI has the value of 5. Okay, that is right here. Okay, RAX is just garbage, so RAX, we'll just say, we'll just not worry about what it is right now. Okay, and then we also have RBX, which happens to be 0 right now, but it's also kind of unnecessary for what we care about right now. So that's where we stand at this point. Okay, we're about to call our factorial, and this is what happens. All right, so let's actually do that. Let's actually call our factorial and see what happens. Okay, if we do SI, okay, well, what happened is now we're in our factorial. Well, some things have changed here. Whenever you do a call, the stack pointer changes. What's the stack pointer now? It's E998, okay, which happens to be 8 fewer than A0, okay? So it's E998, and what I'll do is I'll just say that our I will say that our stack pointer here is going to, I'll fix that in a second. Okay, this was E9A0. Our stack pointer is E998, and what is it pointing to? Well, the hexadecimal value is 0x400575. 0x400575. So what does that mean? Well, guess what? The previous value of, or the return value is after the call from main. Here's where main gets calls our factorial. The return value is 400575, which is what's stored at our stack pointer location. Okay, so that's what we've got at this point. Okay, and let's see all the other variables. Let's see, we've got RDI is still 5, RX is still garbage, and the value of RBX is still 0. Okay, and what are we about to do? We are about to do a comparison. We're going to compare 1 and RDI, and if RDI is less than or equal to 1, we're going to jump to 5F. Well, RDI is not less than or equal to 5, so, or less than or equal to 1. So if we just do this, we will see that we're about to do our comparison. Okay, by the way, we can also print the E flags, right? If we were either less than or equal to 0, we would expect either the 0 flag or the sign flag. But guess what? IF is a flag you don't need to worry about. So there's no sign flag and no 0 flag. Okay, so we can check that. So it's going to skip over this. Okay, and then when we do that, we will get, we're going to go to this push RBX. Okay, so at this point we're going to push RBX. Well, what does that do? It pushes the value of 0 onto the stack and changes the stack pointer down by 8. First of all, it changes it down by 8 and then does that. Okay, so let's actually do that. If we step in, and we now have done what? We have changed the stack pointer to E990. E990. Okay, stack pointer is now down here. All right, and if the stack pointer is down here, and what is at the stack pointer? Well, the stack pointer right now has the value of 0. Great, we just pushed BX onto that value, onto the stack. Okay, why did we do that? Well, we're about to move RDI into RBX. Okay, what does that mean? We're going to move RDI into RBX, so if we do this command, right, watch what happens to RBX. Oh, it becomes 5. Okay, so now RBX has become 5. Okay, and what are we going to do now? We're going to subtract 1 from RDI. Okay, so if we do the next instruction, SI, we subtracted 1 from RDI. Guess what? RDI is now 4. Okay. All right, so then we're going to call our factorial function. Okay, so RDI is our parameter. We're going to now call it with 4. Okay, by the way, so let's put this here. This is the return address for main. Okay, return address in main. All right, so now we're going to call 400546. The next instruction is 400559. So watch what happens when we do this. Okay, we're going to step in. Okay, our stack pointer has changed to 988. E988. Okay, and that's where our stack pointer is now. And what is located there? 0x400559. That's the return address for factorial 5. Okay, it's return address for factorial 5. Okay, well now we're in the midst of our recursive function here. So what's actually happening? Well, we are now about to do another comparison, and we're going to do this comparison now, and again, if RDI is less than or equal to 1, we're going to jump somewhere else, but it turns out it's not. Okay, so if we do SI, okay, we're not going to do that. We're not going to jump. Now we're going to push RBX. Well, if we push RBX, which is currently 5, onto the stack, that's what we're about to do. Let's go ahead and do that. Push RBI. Well, guess what? Now the stack pointer has changed again. The stack pointer is now E980. Okay, and if it's E980 and the value that we just pushed onto the stack is 5. Okay, all right, we're going to use that a little bit later. Okay, all right, so then what are we about to do? We're about to move RDI into RBX. We're about to put our new value. Remember, we're in factorial 4 now, so we're going to just move 4 into RBX because that's what RDI is. Okay, so let's actually do that. We are going to do that, and now RBX has the value of 4. Okay, and what are we going to do now? We're going to subtract 1 from RDI, so let's do that. SI again. We're going to subtract the 1 from RDI, and now RDI is 3, so we can change that over here. Okay, and then we are about to call factorial again. All right, so we're going to call factorial again. Well, what happens when we call factorial again? We change the stack pointer to now point to 978, E978, okay, and now our stack pointer is there, and what's at the stack? 0x, that's down here, 0x400559, 400559, which is the return for factorial 4, that's where it's going to return back to. Okay, and what do we have now? Okay, we're about to do the comparison again. All right, well, 3 is not less than 3 is not less than 1, so we're going to not jump here. Okay, we're not going to jump here. And we're going to then do what? Oh, we're pushing RDX again. Okay, hopefully you're seeing a pattern here. We're going to push RDX, right? Let's actually do it first. We're going to do that. So RDX is now going to go on. Our stack has now gone to E970. E970, and the value that is stored there is 4. Okay, remember the stack gets reused for a whole bunch of different things. Okay, it gets reused for a whole bunch of different things, but you got to keep track of it in these recursive functions each time. Okay, so what's happening now? Well, we are about to move RDI to RBX. We're about to store 3 into RBX because that's our next one. So we're going to do that. Guess what? RBX is now 3, and we've done that. And we're about to subtract 1 from our DI. Let's do that. Our DI is now 2. I'm going kind of fast because we've done this a few times already. Okay, and then RDX is now, or RDI is now 2. Okay, and then we are about to call the function again. Oh, all right, well, when we call the function, what happens? Let's actually look at what happens when we call the function. We are going to change our stack pointer. Our stack pointer is now E968. Okay, so E968 here. And what does it point to? It points to 0x400559. It's the same address each time here because it's the same function. We're just recalling the function each time. This is now the return address for Factorial 3. Okay, and what are we about to do? We're about to do the comparison. 2 is still not less than 1, so we're not going to jump. So here we are not going to jump. All right, so do SI again, and now we're going to push RBX again. All right, this is tedious in this case, but hopefully instruction. Oops, we didn't actually change that, but we're going to push that on there. Okay, we're going to push that on there, and we're going to change the stack pointer to E960. E960. Okay. Oops. Okay, and then now that's where the stack pointer is. Okay. All right, what are we going to do next? We are going to move RDI to RBX. Okay, now we're going to move 2 to RBX, so then that's going to become 2. Let's actually go ahead and do it. Okay, so now RBX is 2. All right, and then we're going to subtract 1 from RDI. Subtract 1 from RDI. And RDI is now 1. And now we're going to call our factorial again. All right, so we're going to call our factorial. And when we do that, we get, what happens? We change the stack pointer to E958, E958, and it's going to have the value of 0x400559. Okay, and now our stack pointer is down here, and now we get to something finally a little bit more interesting. Okay, we're going to compare 1 to RDI and jump if it's less than or equal. Well, guess what? It is less than or equal to 1. So now, when we do the SI, okay, we are going to be on this jump, and it turns out that we better have an E flag of either 0 or sign. In this case, it's going to be 0p $E flags. We better have, there we go, the sign flag has now been set. So PF and IF, but we're not going to worry about those flags. But the 0 flag is set, meaning we are going to jump to 0x4005F. Okay, so let's actually do it. All right, now we are where? We are about to move 1 into EAX. Okay, finally we're moving the value into EAX here. Okay, let's do that. And now EAX has the value of, or RAX has the value of a 1. Okay, and then we're going to return. Why are we returning? Because we just did factorial of 1, which returns if the value is 1, if n is 1. Okay, so we're going to return. All right, let's actually do it. Okay, where do we return to? We return to our IMUL statement. Now we are going to multiply RBX times RAX. Well, 2 times 1 gives us 2. So let's actually do that here. Okay. Oh, by the way, let's see where our stack is at this point. We are 960. We just returned from this one. Okay. So now our stack pointer is pointing to here because we did the return statement, and we are like this. Okay, and the stack bx points, or the stack pointer points to 3 right now. Okay, all right, so now we're going to do this. We're going to multiply rbx times rax and keep the result in rax. All right, so what does that do? It actually changes it. So now look at rax. Rax is 2. That's what we just did with this one. Okay, rax is 2. And then we are going to do this little jump over this business. Okay, we'll see that a whole bunch of times here as we go along. And we're going to jump over, and we are now going to end up on pop rbx. Well, what does that do? That takes the value from the stack and places it into rbx, and then updates the stack pointer. Okay, so let's actually do that. All right, so guess what? rbx now became 3. Our stack pointer is now at E968 here, and we have now a return value there, which is exactly what we want when we are about to return. Great. So we return, and what happens there? Well, our stack pointer goes to E970, okay? And we are going to also be back at another multiply. Okay, well now what's multiplying? Same thing. 3 times 2, because it's going to be bx times ax. Okay, so let's actually do that. 3 times 2, and guess what? Ax is now 6. That's what that did. Okay, and then we're going to jump over again like we've done a number of times. And we are going to pop rbx. Well, when we pop rbx, what happens? rbx it got the value at the stack pointer, so it's going to be 4. And our stack pointer is going to change to E978. And we are going to do what? We are going to return. Great. So if we return, right, we're going to return, and that changes our stack pointer again because we returned to that value. Notice we're at 400,559. That's where we returned to, 400,559. Okay, and we are up here. Okay, and now we're going to multiply again. 4 times 6. Great, let's do it. So we are going to multiply. Now rax is 24. Okay, so that's 24. And we have changed our stack pointer to E980. Sorry, I had it backwards, but I haven't quite done that yet. We are going to jump, and let's see. We are at, we just did what? We just did, we are now at the jump. We just did the imul. Oh, we just did the imul, right. So we have to jump, and then we're going to pop, right. So we have to jump down to here again, like we've done a few times already. And we are going to now pop rbx. So now rbx has now been popped, meaning that rbx is going to be 5. Our stack pointer is now going to be 0, or E988. Okay, and we have this situation here. Okay, and then we are going to return, which means we're going to return back to factorial 5. And so let's do that. Okay, and what happens there? Well, we have to do another multiply. So we're going to multiply bx by ax. Well, 5 times 24. Let's actually do that. 5 times 24 gives us 120 in rax. So that's now 120. Okay. And then we are going to jump over this business again. Okay, we're going to jump over this business again. And then we're going to pop rbx. By the way, when we jumped over, when we did that, we now have our stack pointer E990. So we're going to pop rbx. Let's do that. And rbx became 0, which it didn't really matter because our main wasn't using it, but that's that. And then that means that our stack pointer is now going to be here. Oop. And we now are going to return back to main. And when we do that, we are going to return back to main. Oh, now we're back in main, as you can see here. Okay, we're back in main at 575, which is what we did there. We've actually changed the stack pointer back to the original where it started, and a 9A0, and EAX holds, or RAX holds the value 120, which is our result. Whew. Okay, that was a really short factorial function, but look at how much was going on in the stack. We were storing addresses, we're storing BX values, and so on. And it's saying store the same address each time. Okay, this is why we can come up with stack overflows pretty easily, because if you try to do factorial of 1,000, it would do this 1,000 times, and you might not be able to do that many calculations. Okay, actually, 1,000 is not too bad for factorial. But that's how it works, and hopefully that was helpful.